I'd like to walk through an example of a calculation with a photoelectric effect. And so here is my second take on photoelectric effect, summarizing it with a little bit more information. So our photoelectric effect is proving that our waves of light are actually also particles of light, that there are photons that are packets of energy. And so when one of these photons, let's get a different color, one of these photons hits, so it travels as a wave, it hits the surface of an atom, right? So here's my nucleus, and here's my little electron. When it hits and has enough energy, so the energy of the photon is greater than the binding energy of the electron. And so that electron is bound to this nucleus here by a binding energy, which we're using this variable right here, whose name is escaping me at the moment. Vega? No. When it hits it, if it has the same or equal energy to that binding energy, then the electron flies off. And if it has the exact same amount, it'll do it with a little bit of kinetic energy. But if that energy of the photon is much larger than the binding energy, or just larger than the binding energy of the electron, then that extra energy from the photon, that packet of energy that's hitting the surface of this metal hitting an electron, well, that will just be converted into the kinetic energy of the electron. So an electron, so an ejected electron's kinetic energy is equal to the energy of the photon minus the energy, the binding energy for that electron to the atom. And so remember that when we're thinking about the energy of a photon, we're thinking about this in terms of Planck's constant, which is h, and either frequency, or we're thinking about it in terms of the speed of light and the wavelength of the photon using Planck's constant as well. So let's try applying this into a practice, an example. So we have a microwave oven. It's using energy at or radiation with a frequency of 2,450 megahertz, sorry, which is really like inverse seconds, right? Hertz are inverse seconds. And it does this to warm up food. So what is the energy of a single photon that's emitted within a microwave? And that photon would go and hit your food and convey some energy to it. So let's take down this information. So that frequency is equal to 2,450 megahertz. So a megahertz is 10 to the 6. Let's actually go ahead and convert that. And so that would be 1 megahertz is equal to 10 to the 6th hertz. So this would be times 10 to the 6th over 1 megahertz to give us a value that is 2.450 times 10 to the 9 hertz, or seconds to the -1, whichever you prefer. I kind of prefer inverse seconds because it reminds me that I can use inverse seconds in a dimensional analysis problem. All right, so there's my frequency, and I want to know what the energy of that photon is. So it's going to be equal to, since I know information about frequency, I'm going to stick with the version of this that is Planck's constant times frequency. So that would be equal to Planck's constant, which is our 6.626 times 10 to the -34th joules seconds, times that inverse seconds at hertz, right? So 2.450 times 10 to the 9th inverse seconds. And that's going to give me a value that will have just units of joules. So I'm going to plug that into my calculator. I'm going to pause while I do that. So plugging that in, I get a value that's on the order of 1.6 times 10 to the -24th joules. It's a really small amount, but we're talking about one photon, and they're really itty bitty. And so that's the amount of energy that just a photon in your microwave would have as it heats up food.